This will again be on Painlevé equations.
And thank you for the invitation. I'm always very happy to talk to people across the Pacific. So I'm going to talk about superintegrable systems and this connection between exceptional orthogonal polynomials and Painlevé equations. I think this is a very interesting connection, and I'm happy to see kind of superintegrable systems bridging the gap between these two. Okay, so I'm going to give sort of a brief introduction about superintegrable systems for those of you who haven't heard it, or just a reminder. And then we're going to talk about two rational extensions of superintegrable systems that are associated with exceptional orthogonal polynomials and are also associated with Painlevé equations, Painlevé transcendence, and the way at which you can use this connection to kind of find, in the first case, we'll realize solutions of Painlevé IV in terms of Hermite polynomials, which is a sort of a well-known construction. And then in the second case, we'll be looking at a little bit more a messier equation of Painlevé VI and Jacobi, which is sort of a novel connection. So these are two papers. It's joint work with Ian Marquette and also my PhD student, Lisa Ritter, who is now at NIST in Washington, DC. Okay, so one question that I like to start with is what is superintegrability? And so these are classical or quantum Hamiltonian systems with more integrals of motion than degrees of freedom. Often they're classified by the maximal degree as a polynomial or a differential operator of the set of minimal generating sets of integrals in the motion, right? So if you think about where superintegrability came up, it was looking at systems that were multi-separable. So this was Smorodinsky, Winternitz, and collaborators in the 1960s. And they were looking at second order integrals of motion because those are associated with separation of variables, and trying to classify which systems were multi-separable. So that sort of led to a lot of work on superintegrability in second order, right? So systems with second order integrals of motion. And so we had this separation of variables. So there was a lot of research that went on there and a lot of connection between algebra. So one of the things that I like to think about in superintegrability compared to integrability, right, is the algebra behind it, right? So a lot of the trajectories are exactly solvable, and there's some sort of polynomial or quadratic or Lie algebra behind it. And so it's maybe obvious why you'd want to think about second order superintegrability and how you could use those additional integrals. But once you have higher order integrals, this is giving you some sort of nonlinear symmetry in the system, but it's not super obvious of how you would use them, right? So if I have a third order integral of motion, how can I use that to solve for the trajectories? And why is it useful? And so the answer that I like to think of as a guiding principle is the connection with special functions and the exact solvability, and also the algebra that's associated to them. So many of the special functions of mathematical physics are associated with superintegrable systems. If you think about all of the ASCII scheme of orthogonal polynomials, those arise in different second order superintegrable systems. And sort of more surprisingly, recently there was in the classification work of Winternitz and his collaborators, these Painlevé transcendents come up. And so this is kind of surprising because this is, the classical and the quantum case are very, I want to say classical, but straightforward linear Hamiltonian systems. So the fact that their potential might involve these nonlinear special functions is somewhat surprising, but it's very natural due to the fact that the equations of motion the determining equations for the existence of these higher order integrals of motion are overdetermined And so they end up being nonlinear. So if you look at, say, a superintegral system with a certain type of separation, and you posit the existence of a third or fourth integral of motion, and you try to solve for that integral of motion, you get nonlinear equations, and the solutions of which contain Painlevé transcendence. So I'll make that a little bit or a lot more explicit later. But I think that this is kind of the feel, right? That even though we have these somewhat classic Hamiltonian systems, either in the classic or quantum case, maybe I should be just calling them linear Hamiltonian systems, you're getting these nonlinear special functions and these nonlinear algebras as well. So before I go there, I want to talk a little bit about the exceptional orthogonal polynomials. So these are a new class of orthogonal classes of orthogonal polynomials. Oh, I guess the one downside of having this being full screen is I don't have my nice little block up at the top. And of course my iPad is dead, but okay. You'll let me know if I'm running out of time. I'm a little bit actually more nervous that I will finish way ahead of time. As you see, I don't have too many slides to go over. Okay, so in 2009, David Gomez-Uyate, Nikki Cameron, and Robert Milson started investigating these new classes of orthogonal polynomials and positing what would happen if they had gaps in their degree. So essentially, they're relaxing the assumptions of the classic or Bochner's theorem. So the Bochner's theorem says that if we have a Sturm-Liouville operator that emits polynomial eigenfunctions of every degree, then up to an affine transformation in the independent variable, they're the classical polynomials of Hermite, Laguerre, and Jacobi. Right? So if you're thinking about, say, a one-dimensional Hamiltonian, then there's not much that is exactly solvable in terms of orthogonal polynomials. You know, you have essentially the harmonic oscillators with the Hermite, or you have Laguerre or Jacobi, which would be associated up to some change of variables with something like 1/r potential, or like with having a trigonometric potential, right? And so that sort of is the end of the story. People thought for quite a long time, right? It took until 2009 for someone to say, you know, what happens if you relax this assumption, right? You just have to relax the assumption that there are polynomial eigenfunctions of every degree. So if you relax that assumption, you get new Sturm-Liouville operators that have rational coefficients, and you have new families of orthogonal polynomials. They still form a complete set under a certain choice of Hilbert space, and so on. So there's been a lot, as you can imagine, a lot of research around these new sets of polynomials. So of course, because we know that all of these classical orthogonal polynomials are associated with exactly solvable one-dimensional Hamiltonian systems. And furthermore, in terms of superintegrable systems, we could ask, what is there superintegral systems associated with these exceptional orthogonal polynomials? So this is going back, I guess, 9 years ago, work with Sujimoto and Luc Vinet, where we took exceptional Jacobi polynomials. So essentially you take a Hamiltonian where the wave functions are given in terms of Jacobi polynomials, and you replace that first order Sturm-Liouville equation with the Sturm-Liouville equation for the exceptional Jacobi polynomials. And you get an exactly solvable Hamiltonian. And then the question is it superintegrable? And there's a conjecture which sort of goes the opposite way, right? The conjecture is all superintegral systems are exactly solvable. And so here, this is, you know, supporting the conjecture because you have exactly solvable systems that are superintegrable. So Ian Marquette, also with Christian Ken, did also a lot of work with other systems, looking at the Hermite and the Laguerre cases as well. So here's, you know, the canonical example of a superintegral system is our harmonic oscillator. So it has to have more integrals of motion than degrees of freedom. So First order superintegrability is trivial. So here we have a second order system, and all the systems I'll talk about today are second order. And so the harmonic oscillator, as we all know, has a group symmetry in 2 dimensions. It's rotationally symmetric, but it also has 2 second order integrals of motion, one of which is associated with separation of variables in the Cartesian coordinates. X is associated with separation of variables in polar coordinates. And then this second one, you can make a change of variables to look instead at, I think, probably elliptic in that case. Okay, but here's all the separation of variables: polar, Cartesian, elliptic, light cone, and hyperbolic. The symmetry operators form a Lie algebra. The bounded trajectories are closed in the classical case, and the wave functions are given in terms of orthogonal polynomials. Right, so when you think of the harmonic oscillator, you think about this sort of nice Lie algebra, or maybe the group symmetry. But the point of superintegral systems is a lot of the structure here isn't coming up from the fact that there's a Lie algebra, but there could be a more general polynomial algebra. And maybe there's no group symmetry at all, but as long as we have these higher order symmetries, we'll still have the nice bounded trajectories being closed and this exact solvability of the wave functions. And so when I'm saying exact solvability, sort of what I mean colloquially is that you can express it in terms of a ground state multiplied by an orthogonal polynomial. There's a more precise definition using infinite flags and things like that. But here, if I say exactly solvable, what I'm thinking of is there's a wave, there's a ground state, and then there's some special functions, or in particular orthogonal polynomials, giving us all of the energy states of our Hamiltonian. Beautiful. So what would the exceptional case look like? So our exceptional Hermite polynomials, here's a family. This is sometimes called the state adding case. So there's state adding, there's state deleting cases. This is sometimes called the state adding. So here we're going to start off with the first polynomial, which is just a constant. And then I'm going to create these higher degree polynomials by taking basically a Wronskian, right? It doesn't look like a Wronskian because it doesn't have derivatives, but we can use the identities for the Hermite polynomials to write this way. And so you notice, so this is H. So during Lisa's defense, some people were very upset that there's lots of H's going on, and it's sort of not much I can do about it. So here H is a Hermite polynomial rather than the Hamiltonian in this case. So the block H is a traditional Hermite polynomial, and then the script H is a pseudo Hermite polynomial. So basically, if we skip down to the bottom, if we think about this weight, I'm taking the Hermite weight, and then I'm dividing by the square of this pseudo Hermite polynomial. So a pseudo Hermite just is rotated in the complex plane to guarantee that I don't have any poles. It's still an eigenfunction of my eigenvalue equation for the Hermite polynomials, only it's non-normalizable. Right, so this is why we sometimes call this the state adding. So essentially, I'm taking a non-normalizable state and adding it to the states. Okay, so here we have a ground state, and then then the rest of them will be degrees sort of strictly higher than m. Right, so here you're going to start out with 0, and then you're going to have m plus 1, m plus 2, etc. So here there's gaps in this degree sequence. And they satisfy a second order differential equation, which here I've written it as its eigenvalue equation, and you can see it has rational terms here. So this logarithmic derivative of my rotated polynomial. Cool. So I have some pictures. This is, your standard picture of the regular 1D harmonic oscillator eigenfunction. And they're sort of evenly spaced, associated with the eigenvalue that they're associated with. And so here they all should really be lower in the graph, but I've raised them based on their energy. And then here's our confining potential in purple. probably everyone's well familiar with. And so here is an example of what it would look like if we take what's sometimes called a seed function. So that script that rotated Hermite polynomial of degree 2, and I'm going to put the square of that in the denominator of my weight. And so I get a potential that looks like this. So it has a little gap down here. And then my states all have like one more node than they started with. So this blue state was originally the first order state. The blue state was originally my 0th order state. So it was originally just my ground state. And now it has this little bump. And then here I have this extra state down here. So you see we have our nice sort of energy levels as in the non-exceptional case. And then I have this new added state with negative energy in this case. And you can do this, you can create these exceptional orthogonal polynomials with all different types of degree sequences. Okay, so here I already kind of got ahead of myself. I've already written, what I wrote was a potential. So we want to, as with the classical mechanics we know, we're going to conjugate by our ground state to get a Hamiltonian, which is self-adjoint over the real line, basically, right? So here is, our what would be our kinetic energy. Here's our harmonic oscillator term, and here's the rational extension. And the wave functions are going to be the square root of that weight. So the regular wave ground state of our harmonic oscillator divided by this this real polynomial without zeros because I've rotated it, multiplied by our exceptional orthogonal polynomials. So this is what I'm saying, that it's exactly solvable. So it has a ground state multiplied by orthogonal polynomials. And that's just by construction at this point. So by construction, I've built an exactly solvable one-dimensional system. Asking about one-dimensional systems being superintegrable is trivial, right? So I'm going to look at a 2-dimension. And so what I'm going to do is I'm just going to add on an oscillator in the y direction. Of course, you could do other things. You could take 2 exceptional oscillators in the x and the y and add them together. You could do, there's a lot more that you can do than this first basic kind of toy example. So by construction, the system is exactly solvable, but then the question is it superintegrable, right? So am I able to find integrals of motion, possibly of higher order, probably of higher order, that commute with this Hamiltonian? And so we know it's going to be of higher order because the second order ones are all classified, right? So all second order integrals, superintegral systems were classified in the early 2000s by Willard Miller, Jonathan Kress, who's here, and Ernie Collins. So we know that this is not second order superintegrable. So we say, what is it? Where is it? Or maybe it's not superintegrable at all, but spoiler alert, it is. So let's see. Okay, so one way to see that it's superintegrable is just to directly try to find integrals of motion for it. But in retrospect, and kind of motivating this more difficult example, let's look at it using these ladder operators. Right, so we can factorize the harmonic oscillator via these ladder operators, basically d dx plus x, and then the dagger, the adjoint, would be negative d dx plus x. And these raising and lowering operators allow us to construct additional integrals of motion by looking for polynomials in the generators that will leave the energy fixed, right? So if the A is going to annihilate a state or go down in quantum number and A dagger is going to go up, then I could, if I go up and down, I just have the Hamiltonian x, and I could go up in x and down in y and up in y and down in x. I didn't just say the same thing twice. And we could then look for, in this first case, if I go down in x and up in y, and then down in y and up in x and subtract the two, this would be a skew adjoint operator. So I multiply by I and I get a self adjoint operator. And the same thing, if I take the sum, then I would get a self-adjoint. And if we look at these in coordinates, I get just exactly the integrals of motion that I started from my original Hamiltonian, right? So L1 is going to be the rotation, and L2 is going to be this other kind of particular choice of basis. Okay, so this is something that we all know, but we can also factorize the Sturm-Liouville equation for the exceptional Hermites, right? So we're going to do the same raising and lowering operators. I'm only going to take this this sort of factorized form using this logarithmic derivative of my seed function. Right, so here we have a rational extension of the harmonic oscillator where when I factor it in one direction, I get my classical harmonic oscillator. And when I factor in the opposite direction, I get the exceptional orthogonal polynomial. Okay, so this factorization of my exceptional Hermite polynomial is going to allow me to play the same trick. Right, so we have the factorization of our exceptional orthogonal polynomial, Sturm-Liouville equation. We can combine that. So we can combine those with the ladder operators for our Hermite polynomials. And then we can create ladder operators for our exceptional orthogonal polynomials. Okay, and so we get the same setup. It's got essentially the same algebraic structure, except now we have these higher order integrals that are, oops, sorry, let's go back, that are no longer, so L1, so if we think about these as differential operators, the A's are first order. So if I take an A with an A and then I subtract it in the opposite direction, I have second order, but then I'm essentially taking sort of a Lie bracket, so it gives me a first order. And so here I have an A with an A with an A, so it'll be third order. And so this L1 will be the difference of two third orders, and it'll all work out nicely to be a second order. Whereas L2 will be, oh, sorry. A with an A with an A will be, sorry, will be third order, and it will not work out nicely. In the contrary, L1 will be third order and L2 would be fourth order. Okay, so these additional integrals of motion prove the superintegrability of my original Hamiltonian system. Okay, so now we have a superintegrable system. It's of third order, so it is a third order integral of motion. It's also still separable in polar coordinates because of the construction. And so we might ask, where is this living in terms of our classification of superintegral systems? Right, so already we have a hint that this was related to the Painlevé equation. So it was mentioned first in the 2013 paper of Ian Marquette and Christian Ken when they first studied it. But it came back in 2016 and also 2019. But this is already only talking about the one-dimensional case. But we can see that the Painlevé transcendents come up in a different way by thinking about the two-dimensional case and its superintegrable structure. Okay, so the connection between that comes up through this classification. So there was this effort of classifying second order superintegral systems. So we have a we have a superintegral system with a third order integral of motion. It separates variables in polar coordinates. And this is this classification was done by Gravel in 2004. So in 2004, he looked at exactly these systems. And if you look at his classification, there's no potentials with rational potentials of arbitrary order. Right, so we're taking the logarithmic derivative of the seed function. And so depending on our seed function, we have these potentials that are rational of arbitrary order. And no matter what order it is, I'm still getting a third order integral from this ladder structure. And so if you look at the classification, you see that it's not really in there, right? You can't find these rational potentials. And it took us a little bit to understand, or me in particular, a little bit to understand that these are actually rational solutions to Painlevé IV. So one of the cases that Gravel found in his classification was that the potentials would satisfy Painlevé IV. And so these potentials associated with the exceptional orthogonal polynomials are rational solutions to Painlevé IV. So here, just to cover what Gravel did, he looked at second order 2D Hamiltonian separable in Cartesian coordinates and emitting a third order integral with this leading term. And if you make that assumption, you can express your potential in this form, like this harmonic oscillator piece plus this G term, then G will satisfy Painlevé IV, right? And if G satisfies Painlevé IV, then you will have this third order integral, right? So in our example, we're actually able to just visually connect that this G is this logarithmic derivative of my seed function. And it coincides with the rational solutions of Painlevé IV. So this is very nice. Just to give, I think I probably have a nice little mini conclusion, right? So we are looking at Hamiltonian systems associated with exceptional orthogonal polynomials. We get this whole class of systems with rational potentials of arbitrary order. We look at the classification. We say, well, in the classification, we don't see these rational potentials, but instead we see potentials associated with Painlevé IV. And so then we can determine and verify that these rational extensions are really solutions of Painlevé IV. And we recover sort of known solutions of Painlevé IV. Okay, so that's kind of nice. And it's a nice observation, kind of interesting setup. But I think more interesting, but a little bit messier is what happens when we talk about Jacobi polynomials and Painlevé VI. Okay, so I'm going to start with the Smorodinsky Winternitz singular oscillator. So it's still an oscillator, but now we have these singular pieces. I've lost the group symmetry by introducing these singularities, but it's still superintegrable. So it still has two integrals of motion of second order. Again, to slow myself down, this was one of the potentials from the 1960s, the original superintegral systems that were looked at by Smorodinsky Winternitz. So you lose some orthogonal coordinate systems, but you still have polar, Cartesian, and elliptic. Now you have a quadratic algebra. And so what I mean by quadratic algebra is if I take the commutator with L1 and L2, it doesn't close. I have to add a new integral of motion. I don't write it in here. I just write it as a double commutator. And then once you start taking double commutators, it closes. And on the right-hand side, it closes not linearly as you would with a Lie algebra, but it closes to form a quadratic algebra. Okay, so we have a system that's generalizing the characteristics of a harmonic oscillator, but it's not the group symmetry or Lie algebra structure anymore. It's this quadratic algebra structure that's arising. Okay, but it still has closed bounded trajectories, or all bounded trajectories are closed, and still has the wave function given in terms of these orthogonal polynomials. So I'm going to do the same thing. So starting off with our initial paper, we took a very straightforward construction where we looked at this degree 2. It's not obvious to see, but this is our degree 2, this is a degree 1 Jacobi polynomial, and it's squared. So we're taking this rational extension and we get up a new Hamiltonian. This was one of the ones that was first studied with Sugimoto and Lupine. So its wave functions are going to be the exceptional Jacobi polynomials, and we know that it's superintegrable. So it was shown to be superintegral in the original paper using a similar ladder operator approach as I did before. And that's sort of where it was left in 2013. But more recently, we were able to give a minimal set of integrals of motion. So we were able to find an integral of motion of minimal order. And the minimal order is fourth order. And so we were able to do a similar thing that we did with the harmonic oscillator, right? We found a superintegral system. We know it separates variables in polar coordinates. So I'm able to look at this classification work. So this is a 2017 classification work of Pavel Winternitz, Vieira, and Escobar Ruiz, where they're looking at fourth order superintegral systems separating polar coordinates. This exotic potential means exactly nonlinear potentials that satisfy nonlinear equations. And the potential that that we found satisfies a nonlinear equation, which is called SD1A in the classification of Cosgrove, whose solutions can be represented using backloop correspondence by solutions of P6. So let's look a little bit about generalizing. So here we're going to take this we have a little factor out front, but essentially we're taking a Jacobi polynomial, a logarithmic derivative of my Jacobi polynomial with these kind of ground states out front. And I get a factorization of my Hamiltonian. And this two factorizations, the one factorization giving me the original Hamiltonian and the other one giving me the exceptional, this Darboux transformation, is allowing us to obtain raising and lowering operators just like we did for the harmonic oscillator. Again, I'm sorry, there's it is a messy computation. There's lots of messy equations, but I hope you see this very well-known idea of these raising and lowering operators. Okay, so we do the same thing. We have raising and lowering operators for the different components of the wave function. And so we can play the same trick where we take their difference, multiply by I, we can take their sum without multiplication of I, and we get these integrals of motion. However, this is, again, probably a little bit in the weeds, but this method, I should again say, Kalman, Kress, and Miller sort of pioneered this method, this recurrence relations approach to showing superintegrability, where you're using the recurrence relations of the special functions. They mentioned in their paper that this method is not necessarily giving you minimal order integrals of motion. So I'm probably running out of time. So I will just say that they gave us a way forward. So they gave us a hint of trying to find an integral of motion that's at least a slightly lower order by solving this inverse problem. So here I have L5 is the fifth order integral of motion that I have obtained through raising and lowering operators. And I'm able to sort of solve this inverse problem for L4. There's a little bit of difficulty in there, where you have to replace quantum numbers. So the raising and lowering operators are related to quantum numbers. You have to replace them with their appropriate differential operators. But as long as everything works, it can just go straight through, and you can find this fourth order integral of motion. So if you didn't think that this details are gory enough, you can find them in the paper, right? But we're able to find explicitly a fourth order integral of motion for this entire family of superintegral systems. It's sort of somewhat surprising, I would say, that you have rational potentials of arbitrary order, but still you just have the same structure for the integral of motion. You still have just the same fourth order integral of motion.
About 3-4 minutes, Sarah.
Okay, perfect, beautiful. So now that we have our superintegral system, we know it separates in polar coordinates. We know it has this fourth order integral of motion. And again, I should point out that the leading order term is the same for all of these seed functions, right? So no matter how high of a degree rational extension I have, the leading order term is the same. And the leading order term is telling us where I live in the classification. So if you have a fourth order integral with a leading order term that looks like the square of the rotation generator symmetrized by the difference of px and py, then you can express the potential, making lots of transformations in terms of this Cosgrove SD1A down here. Okay, so what does this tell us? This is telling us that this rational extension associated with our Jacobi polynomials are giving us solutions of this nonlinear equation, which we know is connected to P6. Okay, so here is explicitly our W solution in terms of the logarithmic derivative of my Jacobi polynomials. Of course, it's a little bit difficult, right? Before, when we had Painlevé IV, and we had the Hermite polynomials, you could just pick out how the logarithmic derivative was related to the Painlevé. Here it's of course messier as things are with Painlevé VI, but this connection here is kind of, you can see the connection, right? I like to be a little bit conservative and say, well, I know for sure that this is a rational solution of the Cosgrove equation, right? And in the case that we first studied, we were able to explicitly connect these Painlevé parameters with the alphas and betas of our original equation. So it's got actually a pretty nice, it was a pretty surprising solution, I thought, which gave us some hint that we were kind of on the right track. So these very nice expression of these gamma parameters in terms of the parameters of our Jacobi polynomials. So I'll just end, I think, by showing you some more terrible equations. But this is kind of, if you don't look at what all these coefficients are, and they're a little bit messy. But if you just look at we were able to find the algebra, right? So we have a second order integral of motion associated with separation of variables. We have this fourth order. This fifth order is the one we originally started with the raising operators. And our algebra closes. And it closes not in a Lie algebra, not in a quadratic algebra, but a cubic algebra. And so here, it's a pretty simple cubic algebra where this has only a single cubic term, this L2 cubed. So it's a nice sort of one of the nice examples of cubic algebras and how they're connected to these, to the Painlevé equations and to these exceptional orthogonal polynomials. So again, a lot of words, but I'll just stop and say, what did we do? We're building this interesting connection between the exceptional orthogonal polynomials and the special functions and Painlevé equations. And where does this come from? It comes from going through the superintegral systems. So we take these special functions, we use the exact solvability, we use ladder relations and other algebra relations to prove the existence of these higher order integrals of motion. And then we can use the higher order integrals of motion to determine where in the classification these rational solutions live and to connect them with the nonlinear equations. You can also think of it another way. We know that these higher order integrals of motion, third and fourth and fifth integrals of motion, are determined by nonlinear equations. And so that's another way with which we get these potentials and the nonlinear equations associated with them. So just lots of future work that can be done. Just to mention one, we're only looking at one-step extensions, but you could do k-step. You can have a lot more interesting gaps in the degree sequence. You'll get, I expect, a lot more higher order algebras and different interesting polynomial algebras. And already there's been work into different interesting higher order nonlinear equations with the Painlevé property. So I'll stop here and thank you guys for putting up with me and my technical difficulties.
Thank you, Sarah. Any questions for Sarah? Olga?
Thanks, Sarah, for the interesting talk. So are there any examples known with higher than cubic algebras?
Yes, definitely. So Ian is definitely the Kumu of this, or he knows a lot more. I believe that there's been quadratic algebras, and I also would say that the ladder, this also I think is work of Jonathan Kress. These ladder operators allow you to determine some of the algebra relations themselves also. And so depending on how high up you have to go with the ladder operators, you can get just much higher polynomial algebras. So I believe here, so depending on how many gaps there are in the degree, the polynomial on the right-hand side can be of arbitrary degree. I think that's true to say that in the original paper of Kress, Collins, and Miller, they were able to find polynomial algebras of arbitrary degree.
All right, thanks.
I had a more conceptual question. So when you talk about superintegrability, do you really mean quantum superintegrable systems? Is it, these are all quantum systems, right? you're taking Lie brackets, because I'm more used to kind of having functions on a symplectic manifold and Poisson commuting functions. So if I understand this all right, is there are there kind of classical variants of these systems that you are talking about? Is there a one-to-one correspondence?
There's not a one-to-one correspondence, but there definitely are. And in the classification work, they have been able to find nonlinear potentials that satisfy nonlinear equations in the classical case. I believe that this is an interesting question that I haven't put pen to paper, but I'm pretty sure that if you were to introduce, so here there's no H bar, but if you were to introduce some appropriate H bar in here, the rational extensions would be would have a factor of H bar squared out. And so in the classical limit, this particular example, the rational extensions would disappear in the classical limit. But in the classification of Winternitz and these higher order ones, there are sort of more interesting classical superintegrable systems that are associated with nonlinear equations. And that I think that's also an open question. What is the algebra associated with them? But I would anticipate they would have different interesting nonlinear algebras associated with them as well.
Thank you.
Yes, I have a question. With the usual Lie algebra constructs, there's a lot known about how invariants follow, at least for semi-simple Lie algebras. And so there's a kind of a beautiful theory that you can use. What happens, what is known in the case when you extend that to quadratic or higher degree algebras?
Yeah, so I think that's a really interesting question and a really interesting area of future research. So there's kind of a couple ways to approach it. A lot of ways, or some of the ways that have been done are either just direct classification. So saying, let's look at quadratic algebras with two generators and what are the Casimir invariants of that? What are the representations? And Ian has done a lot of work with cubic algebras and looking at that. But once you get more generators, and of course, there's a lot more you can look at, I don't believe that much is known. Another way of looking at it is looking at these algebras as commutants in universal enveloping algebras of different Lie algebras, right? Yep. So and so that's another approach that there's been a lot of work in that direction. But in terms of sort of an overarching theory or this nice classification work like you have for Lie algebras, that's sort of just a dream in all of our head. A motivating goal, yeah.
With lots of interesting examples.
Yes, exactly. Yep. Thank you. Yes.
Thanks.
Let's thank Sarah again for a good talk.